we're back to the same thing that we were doing before. So this is compilers, and right, so there are few things which are new which I've done. First is this dynamic type checking system which I built. So I think the best one for this is like, okay, I think addition is going to work. So it's one of the helper functions. So you can see over here I've added support for a lot of things. First I've added like floats, integers, strings, all that. And what else was there? Yeah, I also added like functions and lists and all of that stuff. So strings are already there in MIPS, but I'm printing strings as if I would be printing lists, just so that it's easier to do it in the virtual machine when it like comes out. Anyway, what else? Closures, right? So dynamic type checking is a problem actually, because this isn't what the initial plan was. I wanted to build a type checking system which was compile time, and after that it would like generate into code based on the different operand types that it would get. And I instead ended up doing this dynamic type checking thing. So I can show you how the types work. So it's in, I think, syntax.py. So yeah, some random. Okay, so these are my types. My types are integer, float, string, or list. Both are pretty much the same. And then you have algorithms. So the first 3 bits of any value, that pretty much defines the type of that value. And so I'm putting some restrictions on the kind of things that you can input. So like how big can your integers be, how big can your floats be, stuff like that. And then for strings and lists, since these are like heap pointers in the end, so they'll actually have a fixed kind of first 3 bits. So this is stuff that happens in segmentation by itself. Yeah, and so it just turns out that you can actually manipulate the bits correctly. You can manipulate the segment bits so that you'll always have these first 3 bits. And so I have a shell script, yeah, which I'm using to run all of this. And so you can see that I'm setting the segment width using this these options, and that's how I'm getting this thing, this almost deterministic sort of first 3 bits, yeah, like completely defined a type. But this is bad. So dynamic type checking is always bad, because it's not type checking at all. In fact, it's basically like getting the value, and then based on the value you determine what operation you want to do. So it's just writing more code after it's compiled, which is not good. Instead, we want to build a proper type checking system so that we don't have to do this stuff. Now, dynamic type checking can also be thought of as basically static type checking, but where there's only one single type. So for example, when you convert like an integer to a float in a statically typed language, well, that all of that happens automatically, right? So the same stuff happens with dynamic type checking, except you can think that it extends a bit more. So you can have convergence between all sorts of different types, which are not even types, just like different cases of values that you get in your inputs. This isn't how it works in static type checking systems, and that's why static type checking is actually more expressive, because they have multiple types, whereas for dynamic type systems, that's only one type which has different categories based on the value that you'll have, and so it's less expressive. And so we are still in the process of coming up with extensions to our grammar, which will allow us to like taking define types before you generate the code. So with that you can really optimize stuff, and we have to do that because currently it's a bit slow. Okay, anyway, the other thing which I did was enclosures. So for example, if I show you this sample, I think this is sample 5. Yeah, no, okay, this is the assembly code. So it's this thing. So you have f is some algorithm. Inside of that you have g as being another algorithm which just prints the input or whatever, and then you return g, right? And so I'm defining g as f of 1, and then similarly you have h, which is pretty much the same function. All right, it's just the same thing as s, except yeah, so except it has a different address, so it's basically a different function. And then you have k equal to h of g, right? So this you can actually do using inline functions, which I have not done yet, but I should probably be doing this so that you can have different identifiers for the functions, so they are treated as different things, and that would be pretty awesome, because currently two instances of the same function are treated as the same thing. So if I have like I don't know, so let's actually go to some other sample. First let's run this sample, because just so that you can get an idea. So it's going to be run.shell and this thing, so it's samples sample5.txt. right? Okay, it just generated the code, whatever. So it prints, so first it runs k, and all k does is that it prints g, right? Because k is basically an algorithm which prints the a thing, which is like something local to h, and this local thing, by the way, changes a lot. But anyway, the point is that here this local thing is g, the value g basically, and so it just prints that, which is an algorithm. So it prints as an algorithm at some address, whatever, and then it runs g, which just prints 1, because that's what x is for g. Yeah. So this is pretty okayish. I think it's not complicated, except weird stuff starts happening when you reuse functions. So let's say you put f of g, then what this will do is, yeah, it will be the same stuff, because what happens is this x thing is actually local to f. So whenever you'll run g, it will go back to its lexical creator, and then it will look at, oh, what's x? Oh, we have updated x. And so it's a bit of somewhere between lexical and dynamic. So based on the current value of the x, your runtime will be defined. So before it was like f of 1, now it's f of g. So this g overwrites the 1 thing, and that's why you just print g both the time. Same stuff can be shown through a more comprehensive example. Oh, and by the way, these are different functions. Just saying that. Okay, shit. If I use the k thing, these all are going to be like different functions. I'm just gonna print all of this. Oh yeah, okay, this is not correct, because you can't do k of g. K is not a function that can be called with an argument, so it's going to be h of g. Okay, so the first 4 things that are printed, those are different, and you can see that, and then it just prints like g twice. Cool. Yeah, wait a second, where did it print g? It was this one, then this one, then this one. Fine. So it prints g, then it prints g again, because run k is basically that, and then it prints 1 because that's run g. Fine, so that's okay. But if I use f of g, then you'll see that k and g turn out to be the same function. I'm not gonna run this because there's no point in doing that. We just want to look at the identifiers, so the values. So you see that k and g both turn out to be the same value, right? This is an algorithm at this address. It's the same algorithm at that address, and yeah, that's how I've implemented it. So you could either use inlines or something like that, or which I'll put after some point, or you could just say that, oh well, too bad, we'll have to deal with some other data structure to do all of this. We'll have to just use standard stuff that C uses. And yeah, that's this sample. Let's go to some other samples. So this is sample 19, and it's all text files, although it should be like .algl files. So I do have an extension which syntax highlights all of this. Maybe I can use that, but whatever. I don't really care about it right now. So syntax highlights, I think I already made a video on that, so it doesn't matter. So it's going to be sample 19 now, right? So it prints 1 and 2. So first you have f of 1. This 1 is basically what x will refer to now. So x's value is 1, and then it's like run g1. So g1 is just this internal function which it emitted, and then it's going to just run g, which refers to this f's local variable x, and then it just prints that, right? So here it's just going to print 1. Then this prints 2 because g2 is, so you could either think of it as g2 having the value 2 stored somewhere, or in my case f itself has these values stored. Yeah, so if I'm going to run this again, then you'll see that since x was overwritten, so it's not going to print 1, it's going to print 2. And so you have to be careful about all of this. You can't use it to like generate functions. You can only use it for, you know, how do I even say this thing? Yeah, I have no idea how to say this thing. Yeah, so you can't really generate functions like this, because generate functions with different static variables, because that would be a bit like macros, and these aren't macros. Okay, these are functions, so I want it to be like this, and more than that I am too lazy to change it at this point. So the thing I'm using for doing all of this is basically a cactus stack, which is also called a parent pointer tree. So I can go through a bit of code which will probably make you understand. I think this was in the return statement. So return.s, yeah, that's my assembly code. Yeah, so I'm doing all of this. So this basically is going to like create a fake copy of a function's call stack, right? So of a function's stack frame, yeah. And then whenever some other function refers to this stack frame and it's not actually there on the stack, it will just go to the fake copy. And so that way your parent pointer tree, which I'm also creating, by the way, I think in the algorithm definition itself, yeah, I'm adding stuff to the parent pointer tree. And so you can use that to just figure out what the value should be. And well, if the parent is there on the stack itself, you don't do any of that. You just go down and then you search values in that stack frame, and this keeps on going. And so this is running fine so far. I'm not getting all that much of errors. I should also show you like how the strings and all that stuff work, but then that's like trivial. So I had to learn a lot about like these system calls and all that in MIPS, and so they are a bit restrictive because there's only like 1 till 11 till 12 system calls, and then each of them do some sort of thing. So there's one system call which prints strings, but apparently there's no system call which can print like binary values. So I don't know what's going on with them, because then I don't have to print this integer stuff. It's just like I can directly print the binary values, but whatever, doesn't matter. Yeah, and also like you have to initialize the string beforehand, so all of that's messed up. Frankly, I don't like any of it, but yeah. Okay, so this is cool. Right, I also added I think, so maybe I didn't show that, but I also added a whole new class for extending this language in the interpreter way, at least. So the interpreter is still there. It's not like, since now it's a compiler, so it's all going to be like based on this compiler thing. No, you still have the interpreter, and it's very useful, and you can extend the interpreter now because I've made this syscall sort of thing. I think I showed this already, I don't remember it, but you can use it to create all sorts of system calls. I call these system calls when they are really just things which you can't construct from the language itself, and so you construct it from the underlying thing which I use to create this language, right? Create the interpreter, which is Python basically. Yeah, so like a lot of functionalities like reading, writing files, these things are not there in the language inherently, so you have to extend it somehow. So we are yet to add input in the compiled in the compiler, right? So you can actually take user input in MIPS, which is nice, I think, because then you can do a lot of stuff. You can't read files, you can connect to the internet. Those are two major flaws, but then again I don't think we'll actually get to that sort of stage where we have to do any of this. Currently the thing that we want to do is type checking, and then optimization, right? So the reason we want to have optimization is basically because we want to show that there's a speed up that we get when we write stuff in assembly, and currently there's no speed up. There's in fact a speed down, and the problem with this stuff that I've done, this code that I've generated, is that dynamic type checking, it takes up most of the time, right? And because of that, it's slow, very, very slow. And closures and all these things, once again, these require so much of time, so these are like slow things. So yeah, this is it. I'll see you guys in the next video. Bye.